So now the question must have occurred to you to ask the following thing. What happens when you're near a point excluded from the domain of a rational function? Okay, so we saw that rational functions, like let's say f of x is equal to 1 over x plus 2, right? Does that even come out? Yeah. We saw that a function like this might have a domain, well, not might, it would have a domain of negative infinity to negative 2 union negative 2 to infinity, because we're specifically excluding what happens when we're specifically excluding the x value where the denominator becomes 0, right? If you let x equal negative 2, negative 2 plus 2 is 0, so we have 1 over 0, and that's just not tolerable, right? That's just not defined. Okay. But we're very interested to know what happens nearby. Okay? And so we're going to see that what happens nearby is going to be two things. Okay? The two things that can happen near a point where near a point excluded from the domain of a rational function are either that point can be a vertical asymptote, or that point excluded from the domain can be the location. Let me say it again. The point excluded from the domain of a rational function can be either the location of a vertical asymptote, or it can be the location of a hole. Okay? So we can look at these. We can look at the conditions under which we get a vertical asymptote and a hole more carefully. Okay, what are these conditions? Let f of x be our rational function. All x which make both the numerator and the denominator 0 will be the location of a hole. Okay, and any x which only makes the denominator 0 will be the location of a vertical asymptote. Okay. Now we have seen both of these cases in the domain video, but just briefly on the side before I go into my 4 carefully prepared examples, you might say, okay, any x which makes both the numerator and denominator 0 will be the location of a hole. So if you think back to our domain examples, we remember that f of x equals x plus 2 divided by x squared minus 4. We can see that the value x equals negative 2 makes the top 0, but x equals negative 2 also makes the bottom 0. For negative 2 squared is positive 4, and 4 minus 4 is 0. So we can see that at x equals negative 2, we will have a hole. Okay? Okay. Now, any x which only makes the denominator 0 will be the location of a vertical asymptote. Let's look at this one. Okay? F of x equals, let's just say for variety, 1 over, let's say, x minus 2 squared. You can see that the value x equals 2 does in fact make the denominator 0. It does not make the numerator 0, so it falls into this category. This rational function will have a vertical asymptote at x equals 2. Okay? So you can see that both of these kind of cases can be seen. So now I'm going to go to some examples. So now I have these carefully formed examples for us. Okay? Okay? So now let us look at these examples. Okay? If you look at this top example here, if you look at this top example here, the f of x equals to 1 over x minus 3, we can see that at the location where the denominator is 0, that is at x equals positive 3, you can see that if I take 3 minus 3, I get 0. You can see that that value does not make the numerator 0, right? So we remember our condition is that any value of x which makes only the denominator 0 will be the location of a vertical asymptote. So this one has a vertical asymptote, which we're going to abbreviate as v dot a of, and how do we write the equation of a vertical line? X equals a constant. In this case, x equals 3. Okay? So a vertical asymptote of x equals 3. By the way, so a vertical asymptote is a vertical line that the function is going to somehow approach. Okay? We're going to talk about that more specifically later. So let me say in this case, just a vertical asymptote located at for the time being, because we haven't talked about what they are yet, but we're going to say that they're located at x equals 3. Okay. What about example number 2 here? F of x equals, the numerator is x plus 4 times x minus 2, and the denominator is x plus 3 times x plus 1. Now, you might notice all of these are factored on the top and on the bottom. I did this to make our analysis easier for the purpose of this example. You may get them factored or not, but of course with our previous lessons we know how to factor, and so we can always, so I know that you guys can always bring it to this form for the purposes of analysis. But of course, because here we want to talk about these properties, I've already factored them to make the analysis more easy. So if you look at this example number 2, the f of x equals to x plus 4 times x minus 2 divided by x plus 3 times x plus 1, we can see, aha, what are the values that make the denominator 0 here? Well, negative 3 will make the denominator 0 because it will force this first factor to be 0. And negative 1 will make this denominator 0. We'll make the second factor x plus 1 0. If you take negative 1 plus 1, that's 0. And you can see it makes the denominator 0, right? But you will also notice in this example that neither of those values make the numerator 0, right? So what does that mean? That means that we will have vertical asymptotes located at the x values, negative 3, and the x value, negative 1. Here we get something more interesting. I have the rational function x plus 2 times x minus 2 on top, and x plus 1 times x minus 2 on the bottom. And I ask myself, what are the locations excluded from the domain? Because this factors in the denominator, I can see that negative 1 is excluded from the domain, right? Because if you take negative 1 plus 1 is 0, it makes the denominator 0. I can see that positive 2 is excluded from the domain, because if I take 2 minus 2, I get 0, and that also makes the denominator 0. But aha, whereas negative 1 does not make the numerator 0, the 2 does make the numerator 0. So thinking back to our conditions, we see that any x which makes the numerator and the denominator both 0 simultaneously, that's the location of a hole. In this case, we're going to have a hole located, okay, at x equals 2, and we're going to have a vertical asymptote located, okay, at x equals negative 1. Okay. Finally, we come to this example here. Okay. I look at this example, and I see that the numerator is x plus 2 times x minus 4, and the denominator is just x minus 4. So I ask myself, what's happening here? Well, first I look at all the points excluded from the domain. In this case, the number 4 has to be excluded from the domain, because 4 minus 4 is 0, right? But I can see that in this case, the 4 makes both the numerator and the denominator 0, right? And it's the only point we're excluding from the domain. So what does that tell us? That tells us that here we have a hole, okay, located at x equals 4. Okay, we have a hole located at x equals 4 and no vertical asymptote, okay? So we can see the whole spectrum of situations in these four examples. Well, not the whole spectrum. There's other possible cases, but this gives you a feel for what the possibilities are, okay? And in any case, now with respect to what the graph is going to look like near these, let me tell you what's going to happen. A vertical asymptote. So let me draw a picture for you. This picture is not going to be necessarily that big, but it doesn't have to be, because it's just for our purposes, just a brief discussion of what's going to happen. So if I look here at my xy axis, okay, and I imagine the function 1 over x, what's going to happen here is that the graph is going to look like this, okay? You can see that the value x equals 0 is excluded from the domain, okay? And so the x, as I get closer to 0, the y will go off to infinity. Each while this piece of the function is getting closer and closer to the vertical line, x equals 0, but never touching it, because again, the x will never actually, how do you call it? Because we're looking at what's happening as x is getting close to the 0. The same thing as x goes close to the 0 from the left. It'll get the value of this function as x gets closer to 0 from the left will get more and more negative. The piece of the graph will get closer and closer to the y-axis, but it'll never touch it. That's known as asymptotic behavior, okay? And this vertical line, x equals 0, is the vertical asymptote, okay? We're going to see that that's what we mean by a vertical asymptote. And a hole, when we see it in a graph, will literally look like basically an opening, or that's how we're going to draw it. Of course, we know that there's so many real numbers that we cannot possibly actually see that hole, okay? But we know it's there logically, because we know that the function cannot be defined at that particular real number, okay? So this is what a hole is going to look like, and this is what a vertical asymptote is going to look like, okay? Okay, and with that, let me just write this down for you. And with that, we'll continue this discussion with another topic that's going to be associated with the graphs of these functions. Okay, thank you.